Okay, this is the last video. These are momentum and impulse problems, so I'm not going to go through all of these, but I'm just going to go through like part of them. So like this one, compared to a sports car moving at 20 miles per hour, the same sports car moving at 80 miles per hour it's going to end up having 4 times the momentum because they have the same mass, but this one's moving 4 times faster than this one. And momentum is mass times velocity. Okay. Let's see. 2 objects, same size and shape, but they have different masses. A has half the mass of B. They're dropped from a tower. They're going to reach the ground at the same time because of free fall, but one of them has more mass than the other. Okay, so B, which is more massive, is going to have a higher momentum because of M times V again. Let's see. Reason a football helmet is padded. We will talk about this in class. What this does is increases the time of impact. Okay, so when you have a force times time on something, this is why airbags work the way they do, why football helmets work the way they do. What you're doing is decreasing the force of the impact and increasing the time. You're making a lower force over a longer time, and that makes an impact easier to withstand than like a stronger force over a short time. And that's something that we'll talk about. We'll do some activities with that. So some of these on here are conservation of momentum, which we will talk about. Momentum is conserved when we have no net external force acting. So if we just have 2 objects that like run into each other, they each have an initial momentum, and the sum of that is going to be equal to the sum of their final momentum. And that's something that we'll look at also in class, a couple of different ways. But momentum, like energy, is one of those things that gets conserved. So some of these, like Superman is at rest. He throws an asteroid that has more mass than he does. So this one uses conservation of momentum. Like in the beginning, he and the asteroid are both at rest because he's holding it. He's at rest. He throws it. Then they're both going to have some momentum. So Superman's got some momentum. The asteroid's got some momentum. These two are equal to each other because of conservation of momentum. But they're going in opposite directions. So if the magnitudes of these are equal, the asteroid mass is larger. That means it's going to have a smaller velocity. And Superman has a smaller mass and a larger velocity, so he's going to be moving faster after he throws that. Imagine him throwing it. He's pushed backwards as he throws the asteroid forwards. So he and the asteroid are both going to have some velocity. He's going to have more. He's going to be pushed backwards farther faster because he has less mass. Okay, and so these are things that we'll talk about as we go through this unit. There's some other examples on here of similar, like a cannon. The force of the cannon on the ball is the same as the force of the ball on the cannon because of Newton's third law. But because the cannon is much more massive, it's going to have less velocity as it moves backward. Meanwhile, the ball's going to have a lot of velocity as it moves forward because it has less mass. That's kind of similar to what I was talking about here with Superman. Impulse, we're going to talk about how impulse equals a change in velocity. So here's a ball. It's going to bounce down and then back up. It's actually going to have a change in velocity because it's changing direction. So it bounces down at 2 meters per second and then back up at 2 meters per second, but they're opposite directions. So it's actually going to have a change in velocity of 4 meters per second. And then it's going to have an impulse of that change in velocity times its mass. Okay. And these, again, these are, we haven't gotten all this, like this is the last things that we're going to get to, but these questions use conservation of momentum and also impulse equaling a change in momentum. So if you apply a force over a time to an object, you're going to cause its momentum to change. That's really going to make its velocity change because its mass isn't going to change. The last one I'll talk about here are these buses. So we've got a moving bus that runs into a parked bus. So the parked bus has an initial momentum of 0. The moving bus has got a momentum. And then after they run into each other, they're stuck together. So they're both going to be moving. They're both going to have the same velocity because they're stuck together. The mass is going to be the two buses combined. So we've got first bus mass velocity equals combined buses mass velocity. And if we compare, what they're asking is to compare the first bus velocity to the combined velocity, it's actually going to be 1/2 of what it was. Because imagine it's like this bus that was moving is going to give some of its momentum to the combination of the two. That's what's going to make the combination of the two buses move, but they're going to move at half the velocity because now you've got twice the mass moving now that they're stuck together. So that's just a few notes on this page. That's not every single one, but hopefully that helps go through some of them. And these are things that we'll talk about as we finish up this unit over the next week and a half.